When I first decided to come here, I asked the organization sort of, what would you like me to talk about? I mean, after I've been Amazon CTO now for 20 years, we've done a lot of things in those 20 years. Yeah, and so there's a lot of things that we can actually talk about. The one thing that came back in the conversations was that, so Amazon now is 30 years old. Yeah, so Amazon Retail is 30 years old. How did the architecture underneath Amazon evolve? And mostly because, you know, I don't know if you've ever visited this website. By the way, if I look around the room, this website might have been there before you were born. Yeah? For some of you, Amazon.com always existed. That was not the case, of course. Yeah? In '94, when Jeff started Amazon, actually, he wasn't interested in building a bookshop. When Jeff started Amazon, he was fascinated by the internet. Remember, this is 1994. The word e-commerce doesn't exist yet. There's no architecture book that you can buy or, you know, some platform software that you could acquire to run an e-commerce operation. It didn't exist. So Jeff was fascinated by the internet. What are the kind of things that you could do in the internet that you would not be able to do in real life? And he just picked a bookshop, because a really good bookshop has about 40,000 titles in stock, yet there's millions of books out there. So you could build on the internet a bookshop with all the world's books in it. We still haven't reached that point yet, but you know, I think we're pretty good. The big issue, of course, was how do you build something like that? There's nobody had built a web shop before in 1994. And so everything that you'll see has happened, I mean, when you go a bit through the history, you'll see everything that happened at Amazon was sort of that the engineers were so far ahead of their time that they had to invent themselves out of each of the problem spaces that they were in. And interesting enough, many of the paths that these engineers followed actually later became standardized for everybody else. You know, if I think about sort of service orientation or microservices or infrastructure as a service, things like that, all originated within Amazon itself to solve our own problems that we had. And we'll go a bit through that. Now this is the, we go back to 1994, or 96, this is actually old. This is the Amazon.com architecture. Now, a classic. You know, you know, the whole bunch of front-end processors, which we called Obilos. It's a city on the Amazon River, actually. And Obilos actually was a stateless application. And all state was being kept in back-end databases. Now, in the growth issues, we were not necessarily, by the way, Obilos held all code. Not just the website immediately, but it had the workflow processing for orders. You know, it also had part of the supply chain in it, all these kind of things. It was, why? Because they started small. And so everything ended up in this one big monolith, with this whole battery of databases in the back end. And if you think about those databases, they became crucial. The challenge with databases in 1994 was they were not built for the scale of Amazon. So we continuously had to dance around sort of a whole battery of databases that weren't able to scale. And they were right. I remember one of the last issues we had with those databases, not in the particular architecture, is in December 12, 2004. Our custom database runs on a cluster of databases. Let's not mention the vendor at this moment. And it works on a shared disk. And there's a bug in the shared disk tools. And so December 12th, by the way, in those days, there was something called $25 free shipping. And so December 12th was the cutoff date for that. Busiest day of the year. dead in order for the whole day. Later on, the vendor comes on site, and the first thing he said to me is that you should have tested better. I go like, really? You know, we lost millions of dollars here. You know, this is not the right thing to say. But they were right. Because we were running on commercial technology that wasn't built for the scale for Amazon, yet we were using it completely outside of their scope. That drove me to do a deep dive and actually try to figure out, are we using relational stuff? How are we using these relational databases within Amazon? Turned out 70% was key value. Wasn't relational at all. 20% was single table, no relations to other tables. They did a schema though. And it was only 10% that was truly relational, where you would have multiple tables, foreign keys, stuff like that. Now, go back to, and so it turned out that we were just using relational databases because it was the only storage mechanism available. Now, that was just a default hammer. Now, in AWS, I don't know, we have, I think, 13 different specialized databases. So now you can pick and choose exactly what kind of thing you need at the scale that you need it. And DynamoDB, which is the key value store, is just amazing in terms of speed and in terms of scale. Now, go back to 1996, 7, 8. Backend, remember, backend databases, stateless front-end. And it's not just that we actually are filling up the database. We actually start in the UK, and we start in Germany, and we start in France, which basically meant that we were just recopying the databases, but now for different locales. So there's a whole battery of databases in the backend. Now, one of the things that we track at Amazon is sort of developer, I won't call it productivity, but let's say the speed at which our developers can innovate, think about new things. Because remember, this is 98, 99, things like that. We are doing things that nobody else has ever done before. Similarities, recommendations, customers who bought X, bought Y. All this AI stuff actually under the covers that we just don't call AI. Because it just works. And so what you would see over time is that, you know, feature delivery goes great, and at some moment, we see that trailing off. Our developer productivity starts to collapse, basically. And now I know there's a relation to the number of databases that we had in the backend. Why? Because the reliability of the site wasn't actually driven by the front end, because it was stateless. It was all driven by this whole battery of databases in the backend. And the reliability of the site was basically dependent on these databases. So the DBAs that were managing that, they were on the hook for reliability of the whole site. So they became extremely conservative. You wanted to make a change, you wanted the schemas, you had to go through this DBA cabal. Yeah, and they were not happy because they didn't want to make changes because that would sort of bring instability to the overall databases. And so we're getting to this point where we've created this architectural mess, but we couldn't evolve anymore. Basically, we got stuck. And evolvability turns out to be crucial, especially if you work on things for which you really know that you're going to have to change over time. And then, by the way, there is already research from, I think it's the 60s, 70s, around mainframes, where the observation of how clients observe the development of functionality or of the development of applications is that if you do not launch new features, you'll see usage dropping off. We all expect new features over time in our applications. And so, you know, here we're stuck. So, brilliant engineers at Amazon, and I don't know if you want to read this one. This is called the Distributed Computing Manifesto, written by CTO and some of the senior engineers at Amazon in those days. And it really describes how we're going to get ourselves out of this mess. And it became what we now call service orientation. basically cutting off pieces of OBIOS, of the front end, taking the data that it operated on, bringing them together, putting an API on it, and no direct database access allowed anymore. You can see the pendulum swinging. Here, databases are a shared resource, and there's such a bottleneck. Boom, all the way to the other end, where databases are a private resource to that service. It allowed us to do this sort of evolutionary, cutting off bestseller lists, cutting off some other pieces, trying to get experience how this all works. Remember, this is before the word service orientation even existed. These guys are inventing service orientation. There is no book about this. So, we go there. We go from monolith to service orientation. Beautiful. Yeah. And so eventually we've got all the pieces cut off. We made a mistake there. What we had done was a data-driven decomposition. Mostly because we were so focused on the scalability of those databases that we weren't really thinking about what is the right circle around functionality that needs to go with these. And so there were 3 very large data sets: services, customers, items, the catalog, and orders. And so we've done a data-driven decomposition of our code that basically took then the customer master database and all the code that operated on it. And the same went for orders, and the same was for items. Pretty soon, Amazon starts to scale, and those services become as big as that the monolith was before, and we hit exactly the same problem. Now, we should have done a functional decomposition. We should have thought about, yes, they operate on this customer data, but, what are the scaling requirements for each of those individual components that sit in there? What is the security boundary, for example? Because in the customer master service, there's a little piece of software that gets hit on every web page. Yet also in the same service sits the shopping cart. The shopping cart doesn't need to have access to the credential store. Violation of everything that you can even imagine. And so, when we start to realize the mistake that we've made, we start cutting off these ones in much smaller pieces. And what do we put together? Are those things that have the same scaling requirement, same data access requirement, same security requirements. And those smaller pieces then became what we now call microservices. Now, boom. We get ourselves out of this slump of productivity, and our engineers are going fast and moving fast ahead. Until a year or 2 later, we get into the same problem again. Developer productivity starts to drop off. Why? We have the right architecture. Now, it turns out that, most of these microservices, they have a small team. And for most of these microservices, now, there's a certain percentage of work that each of these teams have to do that has nothing to do with the service itself. It's basically managing capacity, managing your databases, managing your data store, and each and every one of those teams has to do exactly the same thing. Really? And I actually thought that we were really good in those days, because if you were one of these services and you wanted to have access to capacity, you would go onto a web page inside Amazon, you would fill out a form, and probably at the end of the day, you would get the capacity that you were requesting. And of course, just before Black Friday, massive spikes in capacity, but it's fine, we've built them. But then, when Christmas will be over, and you would go to this team and say, why didn't you release some of that capacity? And they go like, we have this new thing coming up in March, and we thought, why don't we just hang on to it? And this meant that actually capacity management was driven by engineers, not by business rules. Because in essence, it should be business rules that should determine how much capacity you need for your service. And if we can get this on let's say, on a minute basis, access to capacity, acquire new capacity, maybe we don't need to have the engineers be involved anymore, but we can just have business rules that determine how much capacity. The same went for everybody needed to do database management. Everybody needed to do storage management. So that became internally an infrastructure as a service platform. The things that you now know in AWS were first pioneered in Amazon because we needed to build it for our own engineers, so that they didn't need to manage capacity. They didn't need to manage databases and storage and things like that. And so the problem is really, why is this evolution so important? Especially in a world for Amazon where we're doing every time all these things that nobody else has ever done before. And so you don't know on day one how the architecture is going to look like 2, 3, 4 years from now. You don't know. And the good thing is you realize that upfront. Because by now we realize that. We know that the kind of things that we're building will need to change. So evolvability needs to be a principle of the service or of the functionality when you start off. And it really is a matter of evolve or die. If you don't evolve, you get into this stasis situation, you become irrelevant, and eventual death follows there. So evolvability is crucial. It's a software system's ability to easily accommodate future changes. And that needs to be a conscious decision when you start. And so we have a whole bunch of mechanisms and architectural principles and things like that. And I want to touch on 2 of those. First and foremost, break your system into pieces. Now, I know, there are still some cases where a monolith is the right architectural approach. Really, I'm not opposed to monoliths. As long as that everything that sits inside that executable or inside that environment has the same scaling, the same reliability, the same security requirements. I'm not opposed to that. There is, and especially with some platforms like Rails and things like that, you pretty quickly migrate towards something that is more monolithic than really fine-grained microservices. So the importance there is that really for us was that we need to disaggregate our systems. We need to know that this is something we do upfront. And between those components, we need to have low coupling, but a high cohesion inside those servers. And well-defined APIs. No direct database access allowed anymore. The only way you can get access to data that these servers may be holding internally is through an API. No direct database access anymore, because it's one of our problems. Now, if I think about probably the best example of evolvability in AWS is Amazon S3, the simple storage service. And jokingly, I started saying, like, we started off as a single-engine Cessna, and then became sort of a fleet of 3 737s. And now it's a whole bunch of fleets of Airbus 380s, the biggest ones that you can imagine, while moving customers in real time from airplane to airplane and fueling in mid-air. Remember, with Amazon S3, there is no such thing that you get an email on Friday night that says, we're taking Amazon S3 down for maintenance. That would actually put half of the world to a standstill. But, it needs to be able to evolve over time. Amazon S3 launched with 8 microservices. It's now well over 300. And what do these individual microservices then do? We have new storage classes. We have new policy engines. We now select inside. You can actually use an AWS, an S3 bucket now as a table, basically, or as a database. All this functionality that we started adding has been added, but without ever having to take the system down. And we're moving customers around. So, for example, when we started off with the 8 microservices, we basically just made 3 copies of each object in different data centers, things like that. We started to realize that was maybe a way too expensive approach, and we went to eraser coding. But it doesn't mean that you're going to do recoding all the old objects. That's way too heavyweight. Whenever one gets access, you can recode it. But all new ones actually are coded with erasure coding. So it doesn't mean that you suddenly have multiple storage engines. And then also actually building Glacier, which is sort of the long-term storage engine behind it, and how to move data around. So these microservices have an issue. Or not an issue, they are crucial in the evolution. And important in all of that is to have ownership. Teams own their microservice. You put them in charge. They are responsible for innovating of that particular service. There's no mega architecture or architectural VP or a distinguished engineer that tells people what to do. No, you give ownership to the individual teams. Now, one of the biggest challenges that we have at scale is always reliability. And yes, we have multiple availability zones or data centers, so you can replicate over that. But still, if something happens, you would really like to limit the blast radius. And so, if you think about, earlier days, this may have been one application with a bunch of components in it. You need to scale it. Each of those components need to scale up. And anything that happens to these servers, all customers are affected. So the important part of this is then actually start to break this up into pieces. And each of those pieces is what we call cells. In a cell-based architecture, we spread customers over different isolated pieces of the application. Now, to be able to do this, you need to have a router before that. And the router actually takes, incoming requests and sends it to the different cells. If one of these cells fails, let's say if there are only 3 cells, the other 2/3 of the cells keep working. So the impact on your customers, the blast radius of anything, is just limited. Now, with 3, that doesn't seem too much, but if you have 500 of them, you become more and more efficient in sort of that. And depending a bit what kind of architecture you have, and whether, these are, if you have a regional service, that means you run over multiple data centers. You can have internally, you can actually break cells over over the whole region. Or, if you just want to have individual zonal services, that means they run in one AZ by itself, you can take the same approach. And so how do you route? Well, that all depends a bit on the application, of course. This is the simple approach. CloudFront does this on distribution ID. Route 53 does this on host zones. And actually the backend, the hyperplane that sits behind many of the other services like EC2 and things like that, these cells are reachable by customer account ID. Now, if you think about that, this is actually pretty efficient. So each cell is a self-contained unit, follow the same structure as any of the other cells, and they remain organized and they are predictable. And as new customers on board, you just spread them out over those cells. Of course, then issues like hotspots and other things all become issues, but you do have a tool now to limit the blast radius of anything that happens. Now, you can do a simple one like route on host zone ID or distribution ID. It's much more fun to think about, can we actually do this much better? And so, imagine you have a regional architecture. Before this, there's no cells or anything like that. You have all these cells. If one of these, and the cards and the dices are basically customers. If one of those customers actually triggers a bug, and does retrying, it will take down the whole service. That is absolutely the case. Now, if you can start splitting it up, so the blast radius is all the customers. Now, think about a traditional cell-based architecture like on distribution ID. Whatever comes in at Spades actually goes to the cell that actually handles Spades customers. And again, if something goes wrong, only one of the cells dies, or one of the cells hits the bug, the other cells still could work. And so the blast radius is the number of customers divided over the number of cells. However, you can be much smarter than that, because you can actually make use of math in this. Instead of sort of having one customer per cell hit to one cell, you spread them to 2 or more cells. You do an overlapping of that. Meaning, again, that if one of the customers hits a bug, you see that Spades is actually still served by the other cell over there. Yeah, even though the first cell is down and the other cell is down. So you see a slight decrease in availability for overall customers, but not as bad as in the original one where you only have one customer mapping to one cell. So Spades still works. Now this is really cool, because what becomes the blast radius is actually the number of customers over the number of combinations that you can make. Here, sorry guys, some maths on stage. So if the overlaps in your thing, the shard size is 2, we have got 8 nodes, 2 shards, that's the overlap is 2, there's 28 combinations. Which basically means that if you follow this pattern, only 3.6 of the customers will be affected if one of the cells actually is affected, or one of the customer sets is driven. Now, this is a very small one. If you go to 100 nodes, and you take a shard size of 5, you want to see what the blast radius is? Almost nothing. So this here helps your maths help you actually build a system that is highly reliable over these cell-based architectures. We call this shuffle sharding. And really, it works on your servers, it works on queues. It doesn't need a fault-tolerant client, because you assume that the client is actually retrying. That's actually needed. It needs a routing algorithm, and you need to get the assignments absolutely right. Now, we have a ton of these experiences within Amazon Retail. They're called the Amazon's Builders Library. There's a whole range of Amazon experiences around how we have been building systems over time. QR codes, go there. There are amazing documents in there that show you how Amazon is actually doing CI/CD, for example. Or how to do something called constant work. Amazing stories. Now, one of the things that I learned over time is that constraints breed creativity. And what I mean by that is that before cloud, I had this problem that I had to buy a hardware for Amazon, and you had to be really keen on that. If you bought too much hardware, then the CFO will be unhappy. If you didn't buy enough hardware, customers will be unhappy. So there's this beautiful middle in all of that. And then just before Black Friday, a team would come to you and says, we have this brilliant idea for 50 million free cash flow. If you just implement this one now in the coming 2 days. I go, no, we don't have capacity for it. Always made it work though. Why? Because as engineers, we are massively creative. We know how to work ourselves out of a tight spot. And I think we have the absolutely most amazing jobs in the world. To be honest, we can go to work every morning and be creative. Create something. Who else has that job? Nobody. So, cost was one of those things that in 2012, first reInvent conference, I gave this talk on the whole principles of what I thought cloud development would look like, and one of them was, now you can build cost-aware architectures because you have to pay for each resource that you've used afterwards. Okay, great. Most of my customers ignored this, because now suddenly moving fast and being innovative was way more important. till the global economics catch up with you, and your CFO start asking you, what? Now, one of the first and foremost important there is cost needs to be part of your non-functional requirements upfront. When you start thinking about your architecture, you always need to think about how much is this going to cost me. Next to what kind of reliability, what kind of sustainability, compliance, all these other things that I need to. Yeah, so there's a bunch of laws or lessons that we put together in that. I want to go to number 4 because it's a funny story and it is about my hometown. So it's Amsterdam. In 1972, we had an oil crisis. Don't know if you remember that. There were hijackings and things like that, and oil was down. And what the thing was that only we had carless Sundays in Amsterdam. You were not allowed to drive your car for a day just to save oil. We also did research about which households were using what type of energy. The amazing thing was that there were 2 identical households, 2 identical houses, and the energy would be radically different between the 2. What was the difference? The difference was that the ones that were using more energy had the energy meter in the basement, and the ones that were using less energy had the electricity meter in the hallway. That meant that every time you entered your house, you saw how much energy you were using. That changes behavior. Yeah, and the people that didn't see the energy meter, they just lived as they always used to live. So making things explicit, showing your cost, changes behavior. So there's a whole bunch of other things, how to integrate all of that. The last one is cool as well. Admiral, I forgot what her name is. Anyway, there's this famous quote that says the most dangerous sentence in the English language is we've always done it this way. Yeah? So we're a Java shop, we're really good at Rails. Oh, we've done this before for the other customer. Maybe we can do it again. But especially now these days, it's not only about cost, but also about sustainability. Your choice of programming languages impacts your cost and your sustainability significantly. This is research being done on the energy efficient of programming languages. Yeah? Ruby, Python, 75 times as inefficient as Rust. Yeah, so unfortunately, I'm out of time, otherwise I would be holding another half-hour talk about sort of all the advantages of Rust and how we are rebuilding significant pieces of Amazon.com in Rust. Not only because of its efficiency, but definitely also because of its security properties. Yeah, because you see it sits between C and C++, who are both known to be pretty much a breeding ground for bugs, memory bugs. Rust doesn't have that. Now, you will hate the compiler, though. That's a whole different story. I mean, this is the most picky compiler that you will ever run to in your life. Yeah? So think about that. There are programming languages out there that you can choose to significantly reduce your energy usage as well as your cost. By the way, much of those things you can find back at this website that we created called thevogelarchitect.com. In there is also a bunch of podcasts, the guys from PBS and HBO Max was the last one, where they talk about sort of how they integrated costs in their systems. Now, for us as developers, think back about that Amsterdam example. What are the kind of things that you can do to drive your costs down? And I always thought that putting just a big screen in the developer room of the amount of cost that your development environments are taking. Remember, there's this one thing in the cloud. I mean, in the past, your developer machine would sit underneath your desk and you would leave it running when you go home at night. In the cloud, you can turn off the lights. Yeah? When you go home, switch off your developer environment, and you'll see immediately the cost dropping significantly. Well, I hope that with all of this, I'm giving you a bit of insight. Please visit the Amazon Builder Library. And as always, now go build.